Alright, I'm going to try to be not like Ben Stein about this. I'm going to try to make this a little bit interesting for anyone out there who wants to listen and learn about radio wave propagation. A wave can be defined as a disturbance of either sound, light, radio waves that moves through a medium, whether that be air, water, or vacuum, or wheat stalks moving in the wind would be a good example. The anatomy of a wave, we start the cycle at points A, B, C, and D, which will be on the next slide. They comprise one complete cycle having a maximum value above and a maximum value below the reference line. The above line would be the positive alternation, as you would reasonably predict, and below that line would be the negative alternation. Wavelength is one 360-degree cycle, the distance from one crest of one wave to the next. That would be the wavelength. The distance in space occupied by one cycle of a radio wave at any given instant vary from a few hundredths of an inch at extremely high frequencies to many miles at extremely low frequencies. The expression for wavelength would be the Greek symbol or letter lambda. Amplitude is the height of a wave crest above the reference line, half the distance measured vertically from the crest to the trough. And the frequency is numbers of cycles in a unit of time. That would be known as hertz. That's the name of frequency. How many times that happens per second. And the formula for that, for lambda, or wavelength, that would be the speed of light over frequency in hertz. And you can do this one of two ways. You can either do it by miles per second over frequency or meters per second over frequency. The meters per second over frequency would be 300 million. The transverse wave is a moving wave that consists of oscillations occurring perpendicular to the direction of energy transfer, such as a cork bobbing up and down on the water as the waves pass by, and the cork moves very little in a sideways direction. The succession of the crests and troughs. And radio waves, light waves, heat waves, and the wave. I did not put this slide here. Then there's also the longitudinal wave. These are also known as compression waves. They have the same direction of oscillations or have vibrations along or parallel to their direction of travel. The disturbance takes place in the direction of the propagation. It's also known as compression waves, like I said before, kind of like a slinky. And then there are radio waves, radio frequencies, the RF spectrum. A frequency or rate of oscillation within the range of about 3 hertz to 300 gigahertz. The currents that oscillate at RF have special properties that are not shared by direct current signals. The ease of which they can ionize the air to create a conductive path through the air, and the ability to appear to flow through an insulating material, dielectric insulator or in a capacitor, say. And for the convenience of an RF spectrum, it's divided into the number of bands. Each band begins and ends with a power of 3. If you notice here on the spectrum. All frequencies within each band have similar qualities of propagation. The frequencies are also known as channels. You'll often hear about the FCC fighting over them. There are very little, it's it's very rare a frequency is not used. Very little of the RF spectrum is used. So the competition for the frequency space is very fierce. The allocation is ratified by the international agreement, such as the switch from analog TV to the digital TV. That recent switch that everybody knows about, that you had to get a cable box to receive the used to be analog signals. This frees up the space for our now what we have in our pockets, cell phones. And the radio propagation is a term used to explain how radio waves behave when they are transmitted or travel from one point on the earth to another. The propagation means movement through a medium. During radio transmission, an electric field is generated by the antenna in addition to the electromagnetic field produced. The two fields radiate from the antenna at the speed of light, which is approximately 186,300 miles per second. A little bit faster than my car. Radio propagation is affected by several factors determined by its path from point to point. Radio waves travel to their destination in four ways. Radio waves at different frequencies propagate in different ways. Each frequency band propagates in multiple ways. You have the ground wave or surface wave, that would be the purple arrow. That would be a low to medium frequency. It travels along the ground, bending slightly to follow the Earth's curvature. Weakens quickly and is it's what one hears as a fading signal. We also have a sky wave or ionospheric wave. That would be the red and blue arrows. They're a high frequency. They're refracted or bent back to the Earth's surface by the ionized layers in the ionosphere, and they can bounce for many thousands of miles depending upon the atmospheric conditions. We also have the space wave or line of sight, the green arrow. That would be up in the VHF and UHF spectrum. As the radio signal is transmitted, some of the signal will escape the Earth through the ionosphere and directly from one point to another, or reflected by objects on the ground. This is a line of sight type of wave. Then we have tropospheric wave. You try saying that 3 times fast. The tropospheric bending and ducting, that would be in the lower layer of the Earth's atmosphere. Since radio propagation is somewhat unpredictable, such services as emergency locator transmitters, in-flight communications with transatlantic crossing aircraft, and some television broadcasting have been moved to satellite transmitters. A satellite link, though expensive, can offer highly predictable and stable line-of-sight coverages in a given area. The ground wave, these are the lower frequencies, mainly between 30 and 3,000 kilohertz. These are the MF and LF spectrum, and have the property of following the curvature of the Earth via the ground wave propagation. The MF and the LF travel great distances. HF and VHF travel relatively short distances. A radio wave propagates by interacting with the semiconductive surface of the Earth. The lower the frequency waves, they tend to cling to the surface and thus follows the curvature of the Earth. In mountainous regions, they flow through and around the obstructions. They produce steady communications and navigation because the signals are not blocked by the horizon. They have many limitations, though, including great susceptibility to electrical interference, natural and man-made. There are few channels and lack of global range. The services are now on low frequencies are ADF, Automatic Direction Finder, LORAN, and until recently Omega, which has been decommissioned because it was much too expensive to run. Like light waves, radio waves are affected by the phenomenon of reflection, refraction, diffraction, absorption, and scattering. Many different things going on there. Reflection, I'm pretty sure you guys can figure out what that means. It occurs when a wave meets a plane object that is large relative to the wavelength of the signal, and the wave is reflected with minimum distortion or no change in velocity, similar to a light beam in the mirror. Refraction is when a wave moves from one medium to another through which it travels at a different speed, from a more dense to a less dense, and vice versa. The light or radio wave will bend differently than normal due to the change in speed the light is moving through, such as a light moving through a prism, or like when you put a stick in the water and this stick appears somewhere else. Diffraction. This is the act of bending a wave path when it meets an edge whose dimensions are large relative to the wavelength. It follows the profile of the obstruction, and the amount of bending depends on the wavelength. The higher the frequency, waves are not diffracted as easy, such as light waves. Sound waves, such as behind a wall, of a higher frequency may sound like they're cut out or muffled, while low frequencies pass right through, such as your neighbor stomping on the ceiling. I get that a lot. Can be received well beyond the LOS range. The AM signals tend to travel over mountains to reach far distances, while TV and FM signals tend to be blocked. Then there's absorption. It's caused by waves passing through matter and being converted into heat energy. It's referred to as attenuation, and it also causes signal fading. And scattering. The wave encounters one or more objects, a fraction of the size of the wavelength. The wave becomes fragmented and bounces over wide angles. This occurs more often at higher frequencies, VHF and above. Similar to scattering of a light beam when shown into a fog or mist, and tropospheric scatter, regularly used with higher power transmitting equipment. I have a lot of trouble with that word, tropospheric. Atmospheric regions, that would be the troposphere. Would be my luck that they would put that word in there again. Yes, I am reading from cue cards. Region where all weather occurs. The stratosphere is the region where the atmosphere gases are spread out horizontally. The high-speed jet stream travels in the stratosphere, and the incoming solar radiation creates the ozone layer. Then we also have the ionosphere, the uppermost part of the atmosphere, distinguished because it is ionized by the solar radiation. Located in the thermosphere, provides reasonably predictable means of communicating over long distances using HF signals. The ionospheric modes, such as the skywave. The skywaves are waves that leave the transmitting antenna in a straight line and are returned to the Earth at a considerable distance by an electrically charged layer known as the ionosphere. The ionization levels in the Earth's ionosphere can refract, or bend, the radio waves to return to the surface. Ions in the upper Earth's atmosphere are formed when ultraviolet radiation and other radiation from the sun knocks electrons from the gas atoms. Much short and long distance communications below 30 megahertz depends on bending or refraction waves on the ionosphere. The most common is in the 20 to 30 megahertz range. The communication distances of 2,500 miles are possible with one skip off of the ionosphere. The skip propagation has both minimum and maximum ranges. The area